I just put an assignment in Google Classroom, not an assignment, some material in Google Classroom, which was some videos that I made of me going over the answers to the tests, to the test, not tests. And I want to do a quick check out there to see. Julia, did you finally submit yours?
No, I was gonna do it after, like,
All
we
right.
finish class
So I'm not
next
going
week.
to go over any details of the test then. I don't want to ask Julia to step into the hallway and come back because I might lose her. But I should have emailed everybody your test, and if for some reason you didn't get it and you have questions about it, you can email me. But I'll just plan on going over the problems in more detail tomorrow. And look, let's see, Abby Robbins, are you there? Oh, so Abby, need to get your test done too. And then Charles, I don't know, Charles. Don't expect to see Charles, although he's supposed to be here.
Yeah, I'll
So,
do that today.
what's that? You'll do that
I said
today?
I'll do yeah.
Okay. All right. So this new unit, we did a little bit with torque, and you'll have a chance to ask questions about the homework in just a minute. But the the entire unit really is taking what we learned in the first few units, and putting it in a circular. Just instead of everything being linear, everything's going to be going around in circles. And I know we did a circular rotation unit or a circular motion unit, but most of the time in that unit, we were talking about meters per second, how fast a car was going around in the loop, or how fast a person was moving in meters per second. So we were measuring kind of not exactly linear because it was in a circle, but we were measuring linear movement around a circle. But here we're going to be measuring movement in terms of degrees. And we've got different units for everything. If you look up in the top right, the first column here, these are the quantities we've dealt with before: acceleration, velocity, force, mass, displacement, and then momentum. And all the units for those: meters per second squared, meters per second, newtons, kilograms, meters, kilograms, meters per second. But each of those is going to have its own new analog. It's going to have its own circular, like the circular version of each of these. So there's, instead of acceleration, there's going to be alpha, which is angular acceleration, and that's not going to be meters per second squared, but radians per second squared. So if you look down at the unit circle here, it's going to be the number of radians swept out for acceleration, it's going to be the number of new radians per second swept out every second. And instead of velocity, instead of having meters per second, we're just going to have radians per second. And then instead of force, there's torque, which is newtons times meters. We've already been over torque a little bit, which is it's like a twisting version of force. Instead of mass, we're going to get into a thing called rotational inertia, or moment of inertia, which, instead of, like, if you take my pencil here, if I think of the amount of inertia this has, the amount of inertia is just related to its mass, and it tells me if I push it, if I apply a force, how much this is going to accelerate, or how little it's going to accelerate. So inertia tells me the resistance of something to forces that are trying to accelerate it. But moment of inertia, or this I here, is going to tell us how much things resist being rotated. So that's a little bit of a different thing, but it's a rotational analog of mass. And then this is kind of straightforward. Instead of displacement or distance, we're going to have angles. So we won't talk about how far this wheel rolled necessarily, or how far a point moved in meters, but how many radians this point moved through. And then finally, we're going to have an angular momentum, which I won't really get into because it's kind of harder to visualize. So there's not a whole lot that's new here. It'll just be a different way of looking at stuff we've done before, but it is tricky to think of everything in terms of rotation. And first, if you haven't dealt with radians yet, you should probably stay on the meet. We should talk about that because I'm expecting everybody to already have some knowledge of radians. So this question number 1 here, I won't really ask for answers. Just think in your head, how many radians is 360 degrees? And if you haven't dealt with radians before, if you look over this circle, I'll quickly try to explain, although I'm not a math teacher. If you take the radius, this little red line that represents the radius of the circle, and you drape that radius across here to create this arc, so this is an arc that has the same length as that radius, then this angle right here between this green line and the red line, that angle is 1 radian. And since the circumference of a circle is 2 pi r, then you can take 2 pi of these arcs and stretch them around a circle. So 360 degrees should be 2 pi radians, and then 90 degrees is just going to be half of that. So if that'd be half of 2 pi, which would be pi over 2. And then converting the other way is a little bit trickier. 2 radians is how many degrees? So this is 1 radian. Think about that one for a second. And on that one, I will want to see if somebody can give me an answer for that. Okay, does anybody have an answer? Raise your hand if you know how many degrees this would be. Avery, what do you think?
Would it be 360 over pi?
360 over pi, yeah. So there are a lot of different ways to do that. If you've had pre-calc, you probably are getting to the point where that comes kind of naturally. But if you can just remember that 2 pi radians equals 360 degrees, then you can just use dimensional analysis. So if I'm trying to go from radians to degrees, I can multiply 2 radians by 360 degrees over 2 pi radians, and that gives me 360 over pi. Alright, tests, gave those back. We'll talk about those more in detail, but you can take a look at your test and look at my video, and if you have any questions, like I said, email me, but tomorrow I'll say a little bit more. Hopefully we'll have more people finished with that. And the retake will be Monday for the test. Homework. This is a chance to ask about the homework. I'll put Mr. Pennington's solutions up here. Oh, looks like my GoPro has decided to freeze up, so give me a moment. I don't know why it does that. I had everything going great a little while ago. Oh, crap. Oh no, never mind. Maybe I just didn't click. I was thinking it was because I'm streaming I couldn't get this going. Go over C on the second. Alright, Jack, hold on for a minute. Just got to change this so it's not wide angle, or it's just way too wide. Hello? Still looks like wide angle to me. I think that's going to fix it. Yeah, there we go. Okay. Oh, you know what? These are not the actual answers. Those are just the notes. So you said C on page 2, Jack? Correct? This one? All right. Jack, let me know if I'm wrong there. And this is a good opportunity for me because I want to do this a screwy way and see if I still get the right answer. And before I even get going, let me just click on what Mr. Pennington's answer was, and then we can always look at what he did too, but I'm going to do it a less sensible way, but I think it'll still work. Alright, so he says it's 1.2 meters to the left of the center. That's where he put his fulcrum. So I'm knowing that that's where it goes, I'm not going to put it there. I'm going to put it way over here, where it would just never work. And then do the math, and I think it should work out. So, oh no, click the wrong camera. Such a tempting little thing to click. So I'm just going to say, which you can do for these, just kind of arbitrarily place the fulcrum. It probably is a better idea, if you're comfortable with it, to think through it and try to stick it in the same place, in the right place. But if you're not good at that, you can put it anywhere. Just don't put it at the very end. And I don't really know if it'll work if you put it under an existing force, but I think it would. So let me first explain why Mr. Pennington would put it here. What I like to do is imagine that I have it right under the center. And then I look at my forces over here. I would have 300 newtons, 4 meters to the right, and I would have 200 newtons, 2 meters to the left, and 400 newtons, 5 meters to the left. So the torque definitely wouldn't be balanced here. This would give me 1200 clockwise, and this would give me 400 counterclockwise plus 2000 counterclockwise. So putting it right in the center wouldn't be any good. I wouldn't have to worry about this one, because this weight would be right over the fulcrum and it wouldn't twist the bar at all. So if I want it to balance and I move it farther to the right, that's going to make things even worse, because now I've got another counterclockwise torque. So that's why Mr. Pennington has it somewhere in here. He doesn't know exactly where in here it needs to go, but he knows somewhere, because if he puts it all the way over under this one, then he's just going to have this counterclockwise torque, 3 times 4, which is 1200, but he's going to have this clockwise torque, which would be 200, and this clockwise torque, which would be 6 times 3, which is 1800, so it's got to go somewhere in there. But even if you don't reason through it and you put it in a terribly screwy place like this, it should still work out. So I'm going to make this, I'm going to call this X. And I think that's going to allow me to set everything up. So if I say torque counterclockwise equals torque clockwise, then the torque contributed from this is going to be 100 newtons times X. And that's definitely counterclockwise, because it's to the left of the fulcrum. Everything to the left of the fulcrum is going to make it rotate like this. Everything to the right is going to make it go the other way. 100 newtons times X. And just to keep this simple looking, I'm not going to include units. I'm just going to call this 100x. So this distance from the fulcrum to there is 2 meters plus x. So this is going to be 200 times 2 plus x. And this is 5 meters from the fulcrum plus x. So it's going to be 400 times 5 plus x. And now for my clockwise, there's only one thing that's going to be contributing clockwise, and that's this. So if this is 4 meters and this is x, this would be 4 minus x. So I have 300 times 4 minus x. So I get 100x plus 400 plus 200x plus 2000 plus 400x equals 1200x, or sorry, 1200 minus 300x. If you see me make any obvious math errors, let me know, because I'm going kind of fast. I'm going to keep all my x's on the left side here. Got 100 plus 200, so that's 300 plus that, so that's 700. I'm going to add this to both sides, so I get 1000x over on the left side. And then I'm going to subtract these both from both sides. So on the right I'll have 1200 minus, minus 2000, so I'm at negative 800 over there, minus 400, which is going to be negative 1200. So x equals negative 1200 over 1000, which equals 1.2 meters. So, oh, sorry, negative 1.2 meters. So I get an answer that x is negative 1.2 meters. What the heck does that mean? If I say this is the x is the distance to the right of the fulcrum, then it would be negative 1.2 meters to the right of the fulcrum, which actually means it's over here 1.2 meters to the left of the fulcrum. So negative 1.2 meters right of fulcrum, which equals 1.2 meters left, which I think is what Mr. Pennington said. Let me just check on that. 1.2 meters, I meant not the fulcrum, left of the center, left of the center. Right of center. And maybe another way, if I look at this, I've got 4 minus x. I don't know. That doesn't really help. So probably best to just put it where it really should probably go in the right region, and then we would have called this x, and it would have been positive 1.2 instead of the negative 1.2. Anybody? So Canizaro, does seeing that help?
Yeah, thank you.
Okay, even though it was kind of weird. All right. Does anybody have any questions about any of the other ones? All right. Well, we're going to go on to the new thing then. And the new thing is angular acceleration, an introduction into rotational kinematics. So hopefully you have your packet. This is on page 7 of the packet. And I decided today to be a little bit lazy. I've already got my notes written out, and I would just be, I would just be writing these notes out again. So I think I'm just going to show you the notes I've already written and talk about them as I do. So let's see. I'll uncover just a little bit at a time. So the first thing on here is, what's the definition of angular speed? So this little W, it's kind of unfortunate because we've already got work and we've already got watts, and this looks a lot like a W, but it's an omega, and it stands for angular speed or angular velocity. So if you ever need to know whether I'm talking about watts or whether I'm talking about work or whether I'm talking about omega, you can just ask. But the definition for omega is change in angle over change in time. And you don't, sometimes I wonder whether to really call this the change in the angle. I get hung up on that sometimes. So if we have something that's right here, or maybe this circular object that's right here, and it spins, the whole thing rotates to right there, then it's rotated through that angle. And before we rotated through that, I don't really know that there was an angle to begin with, so to call it change in the angle is a little weird. But if I went from here to there, and then I got this new angle, then the change in angle would make sense. But at any rate, it's radians per second. Those are the units for this. And it's just talking about how many radians something is rotating through or sweeping through every second in a circular rotational pattern. All right. How are velocity and angular speed related? So v, this is the velocity that we've dealt with so far. This would be meters per second. This equals radians per second multiplied by r. So this is a little formula, and generally if you take any of the new angular measurements that we're going to be working with and you multiply them by the radius of the circle that they're rotating through, you're going to get a linear measurement. And this is all kind of sketchy. If you look at Mr. Pennington's work when he does this kind of conversion, we'll have this, which is in radians per second, and then you multiply it by the radius, which is meters, and somehow you get meters per second and the radians just disappear. So that's why I wrote these little notes over here, and this is why I thought I'll just show you what I've written down, because this is pretty good, and I don't know if I'd reproduce this just right. So over on the top right, I've kind of expanded on this. I've got velocity equals, this would be linear velocity, equals angular speed or angular velocity times r. And velocity is meters per second, and angular velocity is radians per second. And if you multiply that by the radius, which is in meters, then you're supposed to get meters per second. But like I was just saying, if you just multiply radians per second times meters, you should get radians meters per second. And that's not what's here. So my version of all this, I haven't found this in the online textbook, is I like to think of r as a ratio of meters per radian. So if you have this circle here, and this is r, then every radian, which is this angle, r tells me the ratio of how many meters this is to how many radians we've swept through. So I think of, at least for in terms of units canceling out, think of r as meters per radian rather than just meters. And then your radians will cancel out and you'll get meters per second in the end. Alright, so if you buy into this, that angular velocity is radians per second, then to jump to angular acceleration, this is alpha, is not too hard. So acceleration is the change in velocity. So it's the amount of velocity that we add or subtract every second. So just like angular speed is the angular distance by which we change every second, angular acceleration is going to be the angular speed that we add on or subtract every second. So it's going to be this whole thing divided by time, so we're going to get radians per second squared. So angular acceleration is the change in angular speed divided by the time. Just like acceleration equals change in velocity over change in time. Now we've got change in angular velocity over change in time. And this is meters per second, so this is going to be radians per second, or radians per second squared. If anything gets confusing, just let me know. If you want me to clarify or slow down, because I'm not really writing, I'm just talking. Hopefully it's helpful. So this next part here, maybe I should remove this and actually do this problem with you. Suppose a teenager puts her bicycle on its back and starts the rear wheels spinning from rest to angular velocity of 250 RPM in 5 seconds. So that's just saying the bike's upside down here. I don't know how to draw an upside down bike, but there we go. The bike's upside down, and maybe here's the pedal. Pedal starts going around, and then the bike wheel starts from rest, and after 5 seconds it's turning at a rate of 250 RPM. And we're supposed to calculate the angular acceleration and show our work. I'm going to start over here by just the formula. Angular acceleration equals change in velocity over change in time, but it's going to be the change in the angular velocity over change in time. And we know the change in time is 5 seconds. But either I need to do what Mr. Pennington does and calculate the whole change in angular velocity here, or I need to get that and then plug it in here. And that's what I'm going to do that separately. So 250 RPM, this is an angular measurement. It tells us not how far a point on the wheel is moving. So if you were riding this bike and you were going at this rate, we wouldn't know how many meters per second you were going. This would just tell us how many rotations are happening. So this is a nice angular unit, but we need the angular unit of radians per second, not RPM. So I'm going to just do a dimensional analysis thing over here. 250 revolutions per minute. And I want to get that, I want to turn that into radians per second. So I can deal with these two things separately. Can somebody tell me how many radians there are per revolution? Anybody? Because I want radians, not revolutions. One full revolution would be how many radians? 2 pi. So I can multiply this by 2 pi radians per 1 revolution, and that cancels out the revolutions. And instead of minutes, I want seconds, which that's a lot easier. So 1 minute is 60 seconds. So that'll cancel that out. And when I multiply 250 times 2 pi, and I'm just going to write radians instead of leaving the R there, and divide by 60, I get 26.2 radians per second. So when Mr. Pennington does this, he kind of just does this all at one time, and I wanted to do that separately. So I'm going to take that and put that in here, 26.2 radians per second. And this says, this doesn't ask for angular speed, it asks for change in angular speed. Is that 26.2 really the change in angular speed? Nod or shake. So what was the angular speed before she started doing this? It was 0. And then it went up to 250 RPM, and that's what I've converted to radians per second. So if you go from 0 to this is the change. So this is okay. This is how many radians per second were added on, because all this 250 RPM, that was what was added on. So the acceleration ends up being 26.2 divided by 5, and that's 5.24. And think about what the unit should be. You can think about it in terms of, okay, Mr. Stapleton told us what the units of angular acceleration are, or you can look at what we're dividing. Radians per second over seconds. So it should be radians per second squared. Oh, and it even tells you, do it in radians per second squared. So there's really nothing new here. This is dimensional analysis. Talked about radians and unit circles, which you should have from some math. This is really just acceleration equals change in velocity over time. But I'm not saying it's not going to be tricky, because it's just sort of, it's new. It's the same stuff, but in a weird way. And that's why we have to practice this. Okay, if she now slams on the brakes, causing an angular acceleration of negative 87.3 radians per second squared, how long does it take the wheel to stop? So this means, try to imagine in your, what does negative 87.3 radians per second squared mean? See if you can just, I don't know if visualize it is the right word, but can anybody describe it just in a basic and intuitive sort of way? Because I think if you can, that'll help you understand this, what's going on here. Anyone want to try? Okay, so let me do it then. Radians per second squared. Oh, wait, somebody wants to? Who was that?
Maybe I'll try.
Okay, what do you think, anyone?
Well, so it's like how with the other acceleration when it's like velocity, or is like, or sorry, it's like meters per second, and it's like increasing at that, like its velocity is increasing that much per second.
Right.
It's like this, but the angular speed is increased, or in this case, decreasing that much per second.
Right, exactly. So just if, for example, to give a concrete example of this, if it was turning 87 radians per second, right now 87.3, in one more second, it will have lost all of that. So this is the number of radians per second, the amount of speed in radians per second that it's going to lose every second. So after 1 second, it will have lost 87.3 radians per second. After 2 seconds, it will have lost twice that. After 3 seconds, 3 times that. So whatever if it's going at a speed of 10 million radians per second, with every second that goes by, we could subtract that until it stops. All right. So to find the answer, how long is it going to take to stop? You could just do what I was saying a moment ago. Look at how fast it's going now, which I calculated already, 26.2 radians per second. And then think, if you subtract this much every second, how many seconds is that going to be? It shouldn't even be a second, because this isn't even 87. So it's just going to be a fraction of a second. But we can just plug into the formula. Angular acceleration equals change in angular speed divided by time. And in this case, I'm actually looking for time. I'm going to solve for time. So the angular acceleration is negative 87.3 radians per second squared. And the change in speed, it's going to lose all the speed that it had before. So I calculated that 250 RPM was 26.2 radians per second. So its change in speed when it stops is going to be negative 26.2 radians per second. Oops, sorry, radians per second. But on the bottom, this is going to be delta t. So to solve this, I would multiply both sides by delta t. So then I get this times t equals that. And then I would need to divide both sides by this. So the answer is just going to be 26.2 divided by 87.3. And that comes out to delta t equaling 0.3 seconds. And I'm going to reveal my cheat sheet again over here. I'm cheating as I go because I'll write this next one in because my cheat sheet's a little bit messy. How are tangential acceleration and angular acceleration related? Sometimes I don't even like to. I don't even like this word very much, but Mr. Pennington uses it, and I think you'll see it in physics textbooks and AP physics if you go on. So it's this: tangential acceleration equals angular acceleration times r. So tangential acceleration is pretty much another way of saying linear acceleration, except we use it when something is going in a circle. So if you did have a wheel spinning like this, and you have a point on the wheel right there, and I want to know how much faster this, if we measure the velocity of this point moving around here in meters per second, and then we measure it again when it's over here and again when it's over here, I want to know how many meters per second it's speeding up every second. So that's going to be in meters per second squared, but it's usually used when something is moving in a circle. So it's moving tangent to the circle. So it's still going to be meters per second squared. And it would be the same as what you would get if you had something rolling across the ground and you were asked for its speed, or the acceleration this way. If you have a ball that's rolling down a hill, the tangential acceleration of a point on the edge of the ball is going to be the same number of meters per second squared as the linear acceleration of the ball rolling down the hill. So anyway, that's AT, that's what that stands for. And then there's another kind of acceleration we've talked about before, just to get the confusion out in the open, and that is centripetal acceleration, which you probably remember we're not going to be doing much with it in this unit. So this, if this is the object and its velocity is going, it's moving counterclockwise like this, then this would be centripetal acceleration, and its tangential acceleration would be in that direction. So the tangential acceleration is angular acceleration, which is the number of radians per second, which it's accelerating, times r. And centripetal acceleration equals v squared over r. So remember the whole mv squared over r thing? If something's moving in a circle, it's accelerating toward the center. At the same time, we never did this because we were doing uniform circular motion, where it's rotating at a constant speed. Things don't have to rotate at a constant speed. They can actually rotate faster and faster and faster, and that's when you get tangential acceleration, which we haven't dealt with yet. All right, one last practice problem here, and this is going to be some practice converting back and forth, or converting forth, I think. A powerful motorcycle can accelerate from 0 to 30 meters per second in about, well, which is about 108 kilometers per hour, or if you multiply that by 2.24, that would be miles per hour, so somewhere around 70-ish miles per hour in 4.2 seconds, which is really fast. What's the angular acceleration of its wheels, which have this radius, and we're going to need the angular acceleration to be in radians per second squared. Show you what. So there are a couple of different ways to do this, and what I want to do is first get the linear acceleration. You don't need to draw this picture, but I'll just draw a little picture over here. This is the motorcycle. The whole thing is accelerating that way, but at the same time we get this tangential acceleration of the wheels going around. And that tangential acceleration and this linear acceleration, they're the same. They're gonna be in meters per second squared. So I'm going to find that first. And I'm just going to write tangential acceleration equals A, which is linear acceleration, which equals change in velocity over change in time. And it's going from 0 to 30 meters per second, so the change in velocity is 30 meters per second. The change in time is 4.2 seconds. So this is, from the beginning of the year, simple kinematics. The straight up acceleration of this. 30 divided by 4.2 is 7.14 meters per second squared. So for every second that goes by, the motorcycle is moving 7.14 meters per second faster, and a point on the surface of the wheel tangentially is moving 7.14 meters per second faster. And now if I want to get the angular acceleration, I can use, well, let me write it a different way. I'll write it the way I'll write it the way I wrote it up here. Tangential acceleration equals alpha times r. So the tangential acceleration is 7.14 meters per second squared, and that equals the angular acceleration times the radius of the wheels. But remember when I was saying that it makes everything cancel out properly? If you don't call this 0.32 meters, but you think of it as meters per radian, because otherwise the units just won't work out. But if you trust in the fact that linear or tangential acceleration equals alpha times r, and you just know what the units of these need to be, it's going to work. So to solve for this, I divide both sides by 0.32. 7.14 divided by 0.32 is I've covered up my answer. I'm going to have to actually calculate it. .3, and this should be radians per second squared. So if you just had meters there, and you divided meters per second by meters, you would get 22.3 over seconds squared. There'd be no radians in there. But if you divide meters per second squared by meters per radian, then you do wind up with this. So that's all there is to this stuff. Your assignment is to do the practice on the back, and it's just more of the same kind of thing. The answers are at the bottom if you want to check yourselves, and if you need any extra help from me, we can talk about them tomorrow. I haven't made a video of this, but I did give you the solutions, so if you look in Google Classroom, you can see Mr. Pennington's solutions, which are worth trying to figure out. At this point, you can go or you can stay. I'll hang out here for a while.